session I explained about what exactly DC triggering. Mainly based on the gate supply, the triggering methods are two types. One is DC triggering and other one is AC triggering. Okay. But in DC triggering, there is some drawbacks are there. What are the drawbacks with the DC triggering that I already explained? That is because of continuous supply, it adds additional power loss, and there is no isolation between the gate terminal and power circuit. Then at a time only one thyristor is triggered. Then average gate power loss and maximum gate power losses are high. That is equal. That means maximum gate power loss. Okay. To overcome those drawbacks, then mainly we are implementing AC triggering. We are using AC triggering. Okay. That is in AC triggering again, pulse triggering is important. So many AC triggering methods are there. We also use sine wave triggering, cosine wave triggering, like that. So many triggering methods also there. Okay. But in AC triggering, the one important triggering method is pulse triggering is more favorable. Okay. This AC triggering. In this AC triggering, mainly concentrate on one is pulse triggering. Concentrate on pulse triggering. Okay. This pulse triggering. This is pulse triggering. Yes, in pulse triggering means the pulses are generated by using the trigger pulse generator. We are using this pulse trigger circuit. We are using like this. We are using a trigger pulse generator. TPG, trigger pulse generator. A trigger pulse generator. Trigger pulse generator. Okay. Then this output of the trigger pulse generator is given to pulse transformer or isolation transformer. These pulses are applied to pulse transformer or this is a pulse transformer or isolation transformer. This is pulse transformer, or it is also called isolation transformer. Isolation transformer. Okay. The output of the pulse transformer or isolation transformer, this is gate source resistance. RS is the gate source resistance. Okay. Then let this is gate to cathode. We are connecting some resistance. Let this is RG, gate to cathode resistance. The purpose of RG that I will explain. This pulse trigger circuit. Okay. Then these pulses are applied to the. Now this current is IC. Okay. Then this voltage is taken as VC, gate trigger voltage. Let this current is IR. Now this current is IS. If this resistance is not present, then IS equal to IC. Now if this resistance is present, then what is IS equal to here? Then IS equal to IZ plus IR. That point you remember. If it is not present, you take IS equal to IC. Then this is the thyristor or SCR. This one trigger circuit. This is trigger pulse generator, pulse transformer or isolation transformer. This theoretical circuit. This is one of the theoretical. The practically, the circuit is redrawn like this. The practical trigger circuit is redrawn. AC pulse trigger circuit is redrawn like this. This is practical trigger circuit. This resistance is R. Okay. Follow like this. Yes. We are using pulse transformer or isolation transformer first. This is pulse transformer or isolation transformer. This practical trigger circuit. Then these are pulses. And this is primary voltage VP. Then this is pulse transformer or isolation transformer. This connected like this. Okay. Also connect. This is thyristor, gate, this gate to cathode resistance is Arch. This gate to cathode voltage is VC. Okay. Across this you also connect one diode. Let this is D1 and this is D2 diode. This is SCR. This SCR is practically, this is thyristor. It is supplied with forward blocking voltage, anode to cathode voltage. This is VA. Okay. Then this is practical trigger circuit. This is practical trigger circuit. Okay. Practical trigger circuit. Practical trigger circuit. This transformer is same. Isolation or pulse transformer. Isolation or pulse transformer. Isolation or pulse transformer. Okay. Now, what is the purpose of using this D1 diode and D2 diode? This is a practical trigger circuit. This is a theoretical circuit. Okay. Then, before that, you tell me, what is the advantage of AC triggering, pulse triggering? What is the advantage of AC triggering or pulse triggering circuit? Tell it. One is, we are generating pulses now. Here also, we are giving the pulses. Means, the gate is triggered with pulse triggering means, is there any continuous supply? We are giving the pulses like this means on. Whenever you want to triggering, then you can give the triggering pulse. Once you start the conduction, trigger is off. Again you want triggering means we are giving the pulses. Again trigger is off. Is there any continuous power supply? No. That's why one advantage is there is no continuous power loss. There is no continuous power loss. There is no continuous power loss. Clear? Next. Because of isolation transformer or pulse transformer, there is isolation between power circuit and gate terminal. But this is not present in DC triggering. Why you are not using transformer there? Yes, we are using DC. DC means we cannot work for DC. That is, transformer cannot work for DC. That's why the purpose of using pulse transformer or isolation transformer is to isolate the gate terminal and power circuit. Hence, there is isolation between. There is isolation between gate terminal and power circuit. Gate terminal and power circuit. Because of which transformer? Yes, isolation transformer or pulse transformer. Isolation transformer or pulse transformer. Next. By using center tapped arrangement at secondary,
Here we have the secondary arrangement now. If you use center tapped arrangement at secondary, at a time, 2 thyristors also triggered. Using center tapped arrangement at secondary, using center tapped arrangement at secondary, S at secondary, at a time, 2 thyristors are triggered. 2 thyristors are triggered. At a time, 2 thyristors are triggered. Clear? Note down this. This is the advantage of pulse triggering, that is AC triggering. There is no continuous power loss. There is isolation between gate terminal and power circuit. Using center tapped arrangement at secondary, at a time, 2 thyristors are triggered. Okay. That's the reason why we are implementing the AC triggering. In that AC triggering, that one is pulse triggering. Now this is the practical trigger circuit. In practical trigger circuit, additionally we are using the diodes and we are also connecting gate to cathode resistance. What is the purpose of using D1 diode and D2 diode in the case of practical trigger circuit? This D2 diode eliminates entering of leakage current into the transformer. Because I told now, gate is very sensitive element. You take care about during the operation of gate terminal. Now, if this diode is not present, under forward blocking mode, under reverse blocking mode, within the SCR, there exists a leakage current. If that leakage current is enter into the transformer, there is a stored energy. During switching of transformer with stored energy, there is a possibility of transient voltages. Because of the transient voltages, that gate terminal may be damaged. That's why the purpose of using D2 diode is it eliminates entering of leakage current into the transformer, because diode cannot allow in the reverse direction. That is what the purpose of D2 diode. The D2 diode is it eliminates entering of leakage current into the transformer. Entering of leakage current into the transformer. That is the purpose of using D2 diode. What is the purpose of using D1 diode, you tell me? Concentrate. Yes. See, for example, first I generated one pulse. I am giving supply voltage. One pulse is generated. That pulse is applied to the transformer. Once the pulse is applied to the transformer, there is a stored energy. For next switching action, I want to apply the next pulse. For next switching action, in the previous switching action, there is a stored energy in the primary winding now. You want to dissipate that stored energy. That's why the D1 diode, for next switching action, whatever the energy stored in the previous switching action, that energy must be dissipated. Otherwise, there is a possibility of transient voltages, large voltages. This D1 diode carries the energy stored in the primary and dissipated in the resistance R. Clear? D1 diode carries energy stored in the primary. Energy stored in the primary and dissipated in resistance R. Okay. Then what is the purpose of using gate to cathode resistance? This is cathode and this is gate. The purpose of using gate to cathode resistance is it bypasses the leakage current. What is the advantage of bypassing the leakage current means? If the leakage current in the SCR is bypassed, dV by dt capability is improved. thermal capability is improved. Okay. Then there is a noise rejection, high noise rejection. That means high noise immunity. The holding current is also improved. Holding current is increased. Okay. All these are the advantages connecting a resistance across gate cathode terminal. Okay. What is the purpose of using RG? It bypass leakage current. It bypass the leakage current. It bypass the leakage current. Leakage current. It bypass the leakage current. Then, if leakage current is bypassed, what happened? dV by dt capability is improved. dV by dt capability is improved. Capability is improved. Then another one is thermal capability is improved. Thermal capability. More thermal capability. It will not causes unwanted triggering. I told now dV by dt causes unwanted triggering. Even thermal triggering is also causes damage or unwanted triggering. Thermal capability is improved. High temperature withstanding capability improved. Then noise immunity. High noise immunity. Noise immunity. More noise rejection. Noise is reduced. The fourth one is IH is increased. Holding current is increased. All these are the advantages connecting the gate to cathode. Understood? How it is happening, that you will see in the production, that in clear I will explain. Okay, but up to now you remember the purpose of connecting the gate to cathode terminal is this one. Okay, this about the practical circuit. Practically we are taking some special care because gate is sensitive in order to protect that gate terminal. Okay, this is a practical trigger circuit and this is the theoretical trigger circuit. Okay, this is the advantage of AC triggering circuit we are using. That means in AC triggering, that is in pulse triggering, we are applying the pulses now. In AC triggering, that is in pulse triggering. Okay, is this clear? Pulses we are applying in a pulse triggering method. In a pulse triggering. Okay, whatever the pulses we are applying in a pulse triggering method. This may be high frequency pulses or it may be a low frequency pulses. Okay. The pulses are maybe like this. Let this is low frequency pulses. Low frequency pulses. Let this time is taken as T on and this time is taken as T off time. Then total time period is T. On time, off time. Or it may be a high frequency pulse triggering. You also apply the pulses like this. These are high frequency modulated pulses. Okay, you can apply the pulses like this. This is low frequency pulse trigger, low frequency pulse triggering, and this is a high frequency pulse triggering. High frequency pulse triggering. Now in general, it may be low frequency or high frequency. In the case of pulse triggering, what is T on here? Gate pulse width. Gate pulse width. Gate pulse width. It is also called gate on time. Gate on time. Gate on time. What is T off? This is off time or non-conduction period. Or non-conduction period. Non-conduction period. Off time or non-conduction period. Okay. Then total time period T equal to T on plus T off. This is time period. Concentrate. Pulse width is different. Time period is different. Pulse width is nothing but on time. Time period is nothing but on time plus off time. Now, what is the average gate power loss? What is the average gate power loss in a pulse triggering? Then average gate power loss equal to average gate power loss. Average gate power loss. PGAV equal to average gate power loss. PGAV equal to. How to define? During total time period is power loss is exist or only on time or only off time? Only on time power loss is exist. Off time there is no gate current. Then there is no power loss. That's why average gate power loss equal to Vg into Ig. This is the total power loss. This power loss is exist only on time, that is T on by T. This power loss is exist. Very, very important formulas. In all the competitive exams, based on this formulas, questions are repeated. Concentrate. More and more concentration is required. Then average gate power loss equal to Vg Ig into T on by T. Then tell me, the average gate power loss equal to this Vg into Ig into T on into this 1 by T is written as F. This is one formula. Average gate power loss equal to Vg Ig into T on into F. This formula you also write like this. Average gate power loss equal to Vg into Ig into on time by total time period is called duty cycle, delta. This formula you also write like this. Then average gate power loss equal to Vg Ig is written as PGM, that is PGM into delta. Average gate power loss equal to PGM into delta. But then what is the delta here? Delta equal to T on by T. This is called duty cycle or duty ratio. Duty cycle or duty ratio, where delta equal to duty cycle or duty ratio. T on by T. That is delta is called duty cycle or duty ratio. Then average gate power loss equal to maximum gate power loss into delta. Then I want to write two formulas here. Then what is T on equal to? T on equal to delta T. T on is written as delta T. What is T on? This is equal to delta T. Then you know, what is T off, you tell me? T off equal to T minus T on, T minus delta T na, then 1 minus delta into T. T on equal to delta T. Then what is T off? 1 minus delta T. Is okay? Now I want to define on time by off time. On time by off time. On time by off time. Electrically, we are calculating on time by off time means it is also called Mark II space ratio. On time by off time is also called Mark II space ratio. Electrical we are talking on off, but in communication system we are on is nothing but a mark, off is nothing but a space. That's why it is also called Mark II space ratio. Then what is the mark? Delta T. What is the space? 1 minus delta T. That equal delta by 1 minus delta. Very, very important. That is Mark II space ratio. Okay. This we concentrate. Every formula is important. On time by off time equal to Mark II space ratio. That is delta by 1 minus delta T. Here I am telling that this is low frequency pulse triggering and this is the high frequency pulse triggering. Okay. But in low frequency and high frequency, which triggering is more favorable? Told already. High frequency pulse triggering is more favorable. Why? If you use the high frequency pulse triggering, the turn on time will be reduced. High frequency pulse triggering is more favorable. That is, in low frequency and high frequency, then which triggering is more favorable? Then high frequency pulse triggering is more favorable. Yes? in low frequency and high frequency. Then which triggering is more preferable means then high frequency pulse triggering is more preferable. High frequency pulse triggering is more preferable. Pulse triggering is more preferable because what is the reason? Because turn on time is reduced. One is turn on time, T on, turn on time is reduced. Within less time, the SCR is turn on time is reduced. Then size of the transformer is pulse transformer is reduced. Pulse transformer is less. Size of the pulse transformer is less. Because of this reason, high frequency pulse triggering is preferable. Why the turn on time is reduced? I told now, high frequency pulses are having high amplitude. Because of high amplitude of gate current, then what is the turn on time? Reduced. That's the reason why if the SCRs are triggered with high frequency pulses, then turn on time will be reduced. Why the size of the pulse transformer is reduced? That means in a pulse triggering, we are generating with pulses with high frequency. If you are generating with pulses with high frequency, then what is the size of the transformer required to operate at high frequency? Yes, the high frequency. If any transformer is designed for high frequency, the size of the transformer is very less. Yes, sir. You seen in power system we are using very large transformer na, that is operated 50 Hz frequency na. What is the size? It is very, very large size. In communication system, in TV and radios also, we are seeing very small transformer. What is the size of the transformer? Very less. The reason is it is designed for high frequency. But in our power system, the transformer is designed for low frequency. That's why if any transformer is designed for high frequency, the size of the transformer will be reduced. That's the reason why if you are operating at high frequency, to operate at high frequency, the size of the pulse transformer is less. Okay, that's the reason why high frequency pulse triggering is more preferable. But point to remember, during high frequency pulse triggering, to eliminate the damage of the gate terminal, always PGAV, average gate power loss, less than or equal to PGM into delta. This condition must be satisfied. Otherwise, because of high power loss, the gate terminal may be damaged. During pulse triggering or during high frequency pulse triggering, which condition must be satisfied? Whatever the average power loss exists during the operation, during triggering, that must be equal to PGM delta, or it may be less than delta, less than PGM into delta. If this average gate power loss is greater than PGM into delta, then SCR gate terminal will be damaged. Because of high amplitudes, high power loss are exist. Okay, this about what exactly pulse triggering. Okay, this mainly these formulas you concentrate. Every formula is important. Concentrate, and based on these formulas also we will see some questions in classroom workbook also. Okay, this every formula is important. Okay, this one is T on equal delta T, T of equal to 1 minus delta T. What is the Mark II space ratio? These formulas are very important. Okay, this about what exactly pulse triggering. That is AC triggering. In AC triggering, that I am explained pulse triggering. Okay. Now, in this gate characteristics itself, I want to explain. I want to write 1 or 2 points with respect to pulse transformer. Some points I want to discuss with respect to pulse transformer. That you will see. What is the purpose of using pulse transformer? All this I want to discuss. Yes. That will see concentrate on pulse transformer.
What is the pulse transformer? Pulse transformer or isolation transformer. Pulse transformer or isolation transformer.
Tell us. What is the main purpose of using pulse transformer or isolation transformer is to isolate gate terminal and power circuit. That is the purpose only. That you see in DC triggering, that is a drawback. In AC triggering, this is the advantage. Understood? That is the main purpose of using pulse transformer. The main purpose of using the main purpose of using pulse transformer or isolation transformer is to isolate gate terminal and power circuit. Gate terminal and power. Parallel you can write gate terminal and power circuit. That is one purpose. Main purpose of using pulse transformer is to isolate the gate terminal and power circuit. Another point. Whatever the pulse transformer or isolation transformer is there, the core of the pulse transformer or isolation transformer is made with the ferrite material, because to reduce hysteresis and eddy current losses at high frequency. Okay, to reduce hysteresis and eddy current losses at high frequency, the core of the pulse transformer is made with ferrite core. It is a ferrite core. Understood? But you know, in power transformer, what is the core of the power transformer is made? That is silicon steel. That is a CRGO steel, cold rolled grain oriented steel. But in the case of distribution transformer, what the core we are using? The core is made with amorphous steel. That you know, selection will be in electrical machines, that you know in detail. But here in our pulse transformer, why you are using ferrite core means to reduce the hysteresis and eddy current losses at a high frequency. The core of the pulse transformer is made with the core of the pulse transformer. The core of the pulse transformer is made with ferrite core. It is made with ferrite core. Ferrite or ferrite material made with ferrite. To reduce hysteresis and eddy current losses, eddy current losses at a high frequency. To reduce hysteresis and eddy current losses at a high frequency. Next. What is the turns ratio of the pulse transformer? The turns ratio of pulse transformer. Turns ratio of pulse transformer is. We can define 1:1, or we can define 1:1:1, or we can define 2:1:1. This is with one secondary. It is with one secondary, and this is with a center tapped arrangement. The turns ratio of the pulse transformer is defined with 1:1. You have only one secondary, that is without any center tapped arrangement. If you use center tapped arrangement at secondary, we can define 1:1:1 or 2:1:1. When we can define 1:1:1 means one primary at a time only one secondary is operated, then we can define like this. This is one primary at a time two secondaries are connected, then we can define 2:1:1. Okay, that means this is the center tapped arrangement. Okay, this is primary. One primary, one secondary is connected, then 1:1:1. We can define like this. If one primary, and 2 secondaries are connected like this. 2:1:1 you can define. That means if only 1 secondary, this is correct. But in these two conditions I given. One primary, at a time only 1 secondary is connected. Even though center tap 2 secondaries having, but at a time only 1 we are utilizing. Then you can define 1:1:1. But at a time 2 are connected, 2 are utilizing. Then it is 2, this is 1:1. Understood? Like that we can define the turns ratio of the pulse transformer. Okay. Then another point to remember with respect to pulse transformer must be designed for high frequency because the size will be reduced. Understood? If the pulse transformer is designed for high frequency, if the pulse transformer is designed for high frequency, then size is reduced. The size of the pulse transformer is reduced. If you use the transformer at high frequency, the size of the pulse transformer is reduced. Clear? Now, if you draw the equivalent circuit of pulse transformer, the equivalent circuit of pulse transformer is given by equivalent circuit of pulse transformer is pulse transformer or isolation transformer. The equivalent circuit of pulse transformer or isolation transformer is, this is resistance now. This you take primary voltage. Let the no load branch parameters are, this is R0 and this is X0. Okay. Then equivalent circuit of pulse transformer, that is referred to primary. I am writing referred to primary. Equivalent circuit of pulse transformer referred to primary. Referred to primary means this is transferred to the primary. If it is transferred to the primary means this becomes RG dash. Then this becomes the voltage across the RG becomes VG dash. Okay. Then what is RG dash equal to? We are transferring secondary to primary now. Then RG by K square. What is VG dash equal to? VG by K. Now tell me. We are representing with respect to refer to primary means this is the equivalent circuit of a pulse transformer. This voltage is taken as primary voltage VP. I am not considering all those diodes. In equivalent circuit you don't consider any device, all these. Okay, just we are writing equivalent circuit. Tell me, if the no load branch is neglected, this is the actual equivalent circuit where K is defined as transformation ratio, where K equal to N2 by N1. If 1:1 is taken, you take K equal to 1, whatever may be. Okay. Then based on that N to N1 ratio, then you can define the K. Then if you neglect the no load branch, if the no load branch is neglected, okay, if the no load branch, if it is neglected, if the no load branch is, then what the simplified equivalent circuit, tell me. This is the simplified equivalent circuit. This is R and this one is RG dash. This voltage is which one? VG dash. Okay, this voltage is VG dash. This voltage is primary voltage VP. This is like this again. This is simplified. Now from this, how to write VG dash equal to voltage divider rule. Then VG dash equal to VP into RG dash by R plus RG dash. Now this is one formula you remember, important, but not framed based on this formula in any computer. But based on this point, already questions are framed in all the computer exam. But based on this equivalent circuit, questions are not framed, but you can expect. Mainly GATE point of view, this concept is important. Then VG dash equal to VP into RG dash R plus RG dash, where K is a transformation ratio that you defined as N2 by N1, that VG dash equal to VG by K. Okay, this about what exactly the concept of pulse triggering, then the points you remember with respect to pulse transformer. With respect to pulse transformer. See, one note you remember here. This note actually I given. We are connecting the gate terminal. Practically, during the connection of gate terminal, this arrangement also we can use. Practically, you also connect one diode like this. This diode is called clamping diode. This diode is called clamping diode. This is called clamping diode. The purpose of clamping diode is, if any sudden change of voltage are appear, the gate to cathode voltage is clamps to 0.5 to 1 volt, or it clamps to 1 volt. Okay, it clamps to 1 volt. The gate to cathode voltage clamps to 1 volt. Okay, clamps to 1 volt. It clamps to 1 volt. Okay, this we also use some special arrangements practically also. Okay, this about what exactly in detail about gate characteristics of SCR. Then what is the types of triggering based on the supply, that is DC triggering and AC triggering. What is the drawbacks with DC triggering? Then what exactly AC triggering? Then AC triggering means pulse triggering is more preferable. What is the advantage of pulse triggering? What is the advantage of pulse triggering? Then what exactly pulse transformer? All these concepts I discussed. Some formulas also I given, that you concentrate. See, another point to remember here. Here I am telling that we are generating the pulses like this. This is nothing but a pulse triggering. But we don't maintain a large pulses. We don't maintain large pulse widths. It is a pulse triggering AC triggering. That's why if we maintain large pulse widths, it is not treated as a AC triggering. That means when the pulse triggering is treated as a AC triggering means if pulse width is less than or equal to 100 microseconds, if the pulse width is less than 100 microseconds, then only pulse triggering is AC triggering. Then only it is treated as a AC triggering. Then you can define the power loss equal to Vg into Ig into delta. Then only power loss is Vg into Ig into delta. If in a pulse triggering, if pulse width is greater than 100 microseconds, if you maintain this pulse width is greater than 100 microseconds, then even though it is a pulse triggering, it is not a AC triggering, then it is treated as a DC triggering. If pulse width is greater than 100 microseconds, then even though it is a pulse triggering, it is not treated as a AC triggering, then it is treated as a DC triggering. Understood? That's why you don't maintain large pulse widths. Because it is a pulse triggering, that's why I want to maintain any pulse width. That is a meaningless. Okay. If it is a DC triggering, if pulse width is less than or equal to 100 microseconds, then only that pulse triggering is treated as AC triggering. Otherwise, it is treated as a DC triggering. Okay. That point also you concentrate. Okay. Clear? All these points important. I told now, if the pulse transformer is designed for high frequency, size is reduced. This concept you know even in missions also. How it is means, you know what is the transformer equation? What I am telling that if the pulse transformer is designed for high frequency, I am telling that the size of the pulse transformer is designed. Then you know that E equal to 4.44 F Bm An N1. This equation you know. Now, without changing any rating, the transformer you want to design for high frequency. without changing voltage rating, the same transformer you want to design for high frequency. Then you tell me, if the frequency is increases, if the same transformer you want to design for high frequency, if frequency is increases, if the frequency is increases, then what is the voltage rating? Increases. But we don't make this voltage rating is changing. We want to maintain voltage rating is constant. Now, without changing rating of transformer, you want to design for transformer high frequency. One method is to reduce the cross sectional area. Then again this E is increases, E is reduces, this E remains constant. This E is remains constant. Then without increasing rating of transformer, in order to design the transformer at high frequency, you must reduce cross sectional area. If the cross sectional area is reduced, what is the volume of the core? Reduced. Once the volume of the core is reduced, then what is the size of the transformer? Then size of the transformer is also reduced. Size of the transformer is also reduced. That's the reason why if the pulse transformer is designed for high frequency, then size is reduced. The size of the pulse transformer is reduced. That's why which triggering is more preferable? Then high frequency pulse triggering is more preferable. With this, the concept of gate characteristics, DC triggering and AC triggering concept is completed. Okay. Now based on this concept, we'll see some classroom workbook questions. In next session, I will continue with classroom workbook questions based on switching characteristics, based on gate characteristics. In the switching characteristics, in the sense turn on characteristics and turn off characteristics, and in the gate characteristics. After completing these concepts, then you go for the another concept with respect to thyristor, that is protection circuit. Protection circuit, in that protection circuit, very important concept is snubber circuit. That is snubber circuit is important for any competitive point of view. Then you go for heating and cooling circuit. Based on snubber circuit and protection circuit, we'll see some classroom workbook questions. Then you go for the protection circuit in the, after that we'll start with the heating and cooling circuit. Then remain still 3 or 4 concepts are there with respect to thyristor. Then only go for next device. Okay, clear? Concentrate on these points.